In this segment, we're going to learn about the relative energies of the different chair conformations. For each cyclohexane derivative, there will be two possible chair conformations. For example, the one on the left and the ring-flipped version of the molecule on the right. These two structures will represent the lowest energy conformations of cyclohexane or cyclohexane derivatives. However, it's not necessarily the case that each of these two conformers are identical in energy. One of those may be lower in energy than the other. The lower the energy of the molecule, the more favorable it is. And typically when we're thinking about what functions molecules may serve and may be useful for and trying to predict their various properties that are related to their three-dimensional shape, we need to know and be able to predict which conformer is going to be the preferred conformation. So the rules that we will use for establishing the relative energies of chair conformations is that the bulky groups prefer to be in the equatorial position to yield the lower energy. So to lower the energy of the molecule or to increase the stability of the molecule, the lowest energy, most stable conformations are going to correspond to those that have the bulkiest group or groups in equatorial positions. We'll decrease the energy and increase the stability of the molecule by placing bulky groups in the equatorial position. The reason that placing bulky groups in the equatorial position is favorable is because if we look at the equatorial position in a molecular model, we'll see that those atoms have more room to spread out and be spaced further away from the other groups, whereas if the group is in the axial position, it will interact and be closer in space with the other groups that are in the axial position as well. So by putting the groups in the equatorial position, that gives them more room to occupy and hence minimizes the so-called steric hindrance. The steric hindrance is the crowding of the atoms within the molecule. So bulky groups are going to prefer to be in the equatorial position. So if we look back at thinking about the energy of these two conformers of 1-methyl cyclohexane, and we're trying to predict which of those two would be the preferred conformation, we notice that in the structure on the left, the bulkiest group in the molecule is the CH3 group, the methyl group, it is axial. On the right, it became equatorial because that's what happens when you do a ring flip. All the axial groups become equatorial and vice versa. And so therefore, the structure on the right would be the structure that is the preferred structure, the preferred conformation, because this is the one that is lower in energy. So this is going to be a preferred conformer because it is the one that is lower in energy, because it has that bulky group in the equatorial position. Now, what happens if we have two groups bonded to our ring within the molecule? What is the case then? So let's take a look at an example problem here of predicting the lowest energy conformer of a molecule that has multiple groups. So what we're going to try to do here is draw the lowest energy structure for 1-isopropyl, 2-methyl cyclohexane. And that 2-methyl cyclohexane is one word if you go back and think about your IUPAC nomenclature for this. So we want to draw the lowest possible energy structure for 1-isopropyl 2-methyl cyclohexane. So what we need to do here is draw in our template for a chair conformation. And we could draw either of the two templates out, the one here that I like to think of as kind of leaning toward the right, or we could draw the one that leans kind of toward the left in our structure. Either or will work here. Draw one of those templates, plug in all of our axial groups and all of our equatorial groups. I'm going to go in and draw my axial up, down, up, down, going all the way around the ring. I'm going to go back and erase that little bit here to emphasize that that bond axial is in front. And I could go in and further emphasize that these bonds here are in front by making them into these wedges pointed toward us or in front of us. And then I'm going to go in and fill out my equatorial positions as well. And I'm going to show the equatorial positions in blue here. So go ahead and fill in equatorial down, equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. And now to draw out the lowest energy conformer, lowest energy possible structure for 1-isopropyl 2-methylcyclohexane, we would want to put both of these groups in equatorial positions to make the lowest energy structure that is possible for this molecule, period. So the lowest energy structure possible for a molecule called 1-isopropyl 2-methylcyclohexane has to have all of the bulky groups equatorial, because that's going to allow those to be spaced away from the rest of the molecule as far apart as possible. So our equatorial bonds are in blue here, so I'm going to put at carbon number 1, which by convention is that upper right corner, I'm going to put my 1-isopropyl group there, so CH and then CH3 2 to give me that 3-carbon group where it's the middle carbon of the 3 that is bonded to the rest of the molecule. At carbon number 2, we want to put a methyl group, and that needs to be equatorial as well. So we'll go ahead and put that at carbon number 2. The rest of those groups that I've drawn as lines, we can show as hydrogens. And by the way, if you leave these lines off entirely, that's an abbreviated way to show the structure, and it's implied that there are staggered bonds to hydrogens at all of those positions if you just omit them. So that's okay as well. So as a follow-up to this question, now that we've drawn the lowest energy possible conformer of a molecule called 1-isopropyl 2-methylcyclohexane, the next thing that we need to do is let's do a ring flip. So we're going to show the ring flipped structure of this molecule. So we're going to show the ring flipped structure, and we'll go ahead and draw that down below here because we have a little more room. So I'm showing my equilibrium arrow. I'm going to just write the word ring flip to emphasize that this is the physical process of rotating around carbon-carbon bonds to go from one structure to another. We're not breaking any bonds here and doing it, we're just rotating around them. And to show the ring flipped version, typically what I'm going to do is show my bonds oriented in the opposite direction there, so angled left rather than right. Draw in the rest of my groups here, rest of my bonds, like so. Then I'm going to go ahead and fill in the axial and equatorial groups, and since we have done a ring flip here, what I'm going to do is take all of my blue bonds that were equatorial to start with, and I'm going to convert those into the axial positions. I'm just going to draw my bonds in blue here, axial, alternating up, down as we go all the way around the ring. And then I'm going to put my black bonds as my equatorial bonds this time, now that we've done this ring flip. So I'm just following the criteria here for drawing these bonds. So I've drawn those 6 bonds in. And by convention, once we've done this ring flip, usually what we do is place carbon number 1 down here. Carbon number 1 was what had the isopropyl group directly bonded to it. That isopropyl group started off as equatorial, so therefore it needs to now be axial, because by definition, when we do the ring flip, axial becomes equatorial and vice versa. So we fill in that isopropyl group. And then at carbon 2, typically we number around the ring here in the clockwise direction, so carbon number 2 would be right here then. And carbon number 2 needs to have a methyl group on it. The methyl started off as equatorial up in the top structure. Now it needs to be axial instead. So we'll go ahead and plug that into our axial position because it started off as equatorial, and now it needs to become axial to represent that we've done a ring flip. So in this unit, we've highlighted the relative energies of the 2 different chair conformers of any molecule. Whenever you have a starting structure, you can always do a ring flip on that starting cyclohexane derivative and make the ring flip version compare the 2 to determine which of the 2 will be lower in energy. The lower energy one is going to be the one that puts the bulkiest group in an equatorial position, or the bulkier groups in an equatorial position. So in the next segment, what we're going to look at is we're going to add some additional elements to this puzzle, where we're going to be looking at the concept of stereochemistry as it relates to cyclohexane chair conformation. Stereochemistry is an additional aspect of the 3-dimensional structures of these molecules, where we're going to be able to describe molecules as having a stereochemistry that is either cis or a stereochemistry that is trans. And we're going to see that by ring flipping, we aren't ever going to be able to switch between these cis and trans molecules. We're going to add that element into this puzzle in the next unit, so stay tuned for that.